Okay, I'm going to just switch off my camera to save bandwidth. Yeah. Yeah, hello everyone. Yeah, my name is Hubert du Pontavice, and I'm a postdoc at Princeton University and at the NOAA Northeast Fisheries Science Center. And yeah, thanks Emily for inviting me to give this talk. Today, yeah, I'm glad to present some of the work I've done on the elected founder stock assessment. So this is a collaborative effort. So I would like to start by acknowledging my collaborators on this project. So Dean Sabat, Tim Miller, Brian Stock, and Andrew Minchen. Since 2 years, we've worked on incorporating environmental effects from ocean models to improve fish stock assessment on the northeast coast. So this study focused on one of the yellowtail flounder stocks on the northeast shelf, and we used WAM, a new state space assessment framework developed by Tim Miller and Brian Stock and other colleagues at the Northeast Fisheries Science Center. In this project, we have also built a bottom temperature product to meet our needs in terms of environmental data. So in this presentation, I'm going to talk about the methods to build this temperature product, how we use this product to develop environmental indices, and how we incorporated these indices into a state space assessment framework. So today, there are more and more recommendations to consider environmental conditions in stock assessment. And one of the reasons is that climate variability and directional changes in ocean conditions may lead to changes in productivity through variation in biological parameters or processes, such as recruitment, growth, mortality. And this is particularly concerning in the context of climate change, which could impact a wide range of biological processes. But on the northeast coast, even though fishery scientists have long known about important drivers of time-varying processes, the majority of stock assessment models assume that species ecosystem relationships are stationary over time. So these potential relationships were not directly accounted. And if these relationships are strong, this could result in large uncertainties in stock assessment, with assessment models having notably retrospective patterns. So, for example, here on the plot, you can see spawning stock biomass for the Gulf of Maine cod and its retrospective patterns. Here, in fact, yeah, retrospective patterns are basically when you add or remove years of data to the assessment model, some of the key quantities that change. It can be SSB or recruitment. And these uncertainties could cause misperceptions of stock status and ultimately could have impact on catch advice and undermine the ability to achieve the goal of sustainable fisheries management. But for some years, things are turning around, and I'm going to try to present today one aspect through one example of the incorporation of environmental conditions on the northeast shelf. So, how can the environment be incorporated in the stock assessment? Here you can see a nice illustration produced by Abigail Tarrell and colleagues, who did a great work on ecosystem and socioeconomic profiles on the northeast shelf. I think that illustrates well the different ways of integrating the environment in assessments. First, environmental and ecosystem information can be incorporated to inform uncertainties and provide additional context for the stock assessment. But environment can inform the assessment model in more direct way. It can allow to explore the assumptions of the model and address questions like, is the model consistent with the stock life history? Environment can be also used to investigate the modeling choices, and especially regarding the parameters, such as natural mortality or catchability, which can be directly affected by variations in environmental conditions. And finally, environmental drivers or indicators can be directly incorporated in the stock assessment model. And these different ways depend on the level of knowledge on the ecosystem and stock dynamics, the available data, but also the modeling platforms to integrate the environment. In our work, we are focused on incorporating environmental covariates in a stock assessment model because it's one of the top priorities for the Northeast Regional Action Plan, and because a new state-based stock assessment framework, which has the capability to incorporate environmental covariates, was recently developed. And we used the Southern New England Mid-Atlantic Yellowtail Flounder stock as our case study. But before I talk about the Yellowtail Flounder case study, a little bit of background, even though I'm sure many of you are familiar with. So on the map here, you can see the Northeast US Shelf, which comprises the Mid-Atlantic Bight here, Georges Bank here, and the Gulf of Maine right here. So the region is at the interface of two major currents, the warmer, saltier Gulf Stream, deriving from the south, and the colder, fresher Labrador current deriving from the north. And on the Mid-Atlantic Bight, a cold pool is formed seasonally after each winter, just right here. This is a critical habitat for many key commercial species, including the yellowtail flounder. So the impacts of the cold pool variability on this species will be the case study of this presentation. In this region, there is a long history of fishing. This sector is very important socioeconomically for communities. As you can see on this two-time series, showing the historical landings for Georges Bank haddock stock and the Gulf of Maine cod stock, we have a long fishing history. And currently, the Northeast US continental shelf is one of the most productive marine regions in the US, accounting for one-third of the US fisheries and supporting highly valued fisheries such as sea scallops or American lobster fisheries, as well as many groundfish fisheries. Now let's focus on the changing ocean on the North Sea Shelf. So the North Sea Shelf has experienced rapid warming related to climate change, with a short and long-term increase in surface temperature, but also in bottom temperature. Over the last 3 decades, ocean temperature in the region has warmed faster than any other marine region in North America, as you can see on this map here, with the anomaly in bottom temperature. If now we look at the long-term trends, we can see that bottom temperatures have substantially increased at rates between 0.3 and 0.4 degrees Celsius per decade, depending on the subregion on the North Sea Shelf over the past 64 years. You can also see a robust warming acceleration in the beginning of the 2010s. Yeah, for example, here in the Gulf of Maine. And one of the drivers of this recent enhanced warming on the shelf is a northern shift of the Gulf Stream, which started around 2008, 2010. And regarding the projections, a recent study based on a high-resolution global climate model suggests that the warming rate will be 2 to 3 times faster than the global average. So in this context, our project was focused on the southern New England Mid-Atlantic Yellowtail Flounder stock, and this stock experienced strong variations in stock productivity over the past 40 years. So this flatfish species experienced overfishing from the 70s to the mid-90s, and at the same time, recruitment has declined since the 80s. And from 1990 onwards, recruitment has remained dramatically low, as you can see here. And the stock status is listed as overfished, with spawning stock biomass below the management target, as you can see on this plot. As a result, the catch has dramatically decreased and is today close to 0. So now this stock is currently in a rebuilding plan with a rebuilding date of 2029. In terms of assessment, this stock is assessed using the age-structured assessment program, ASAP, which is a statistical catch-at-age model. And in the assessment, one of the major sources of uncertainty is the cause of the persistent low recruitment in recent years. So in our work, we focused on this population process. Recruitment of this stock depends on temperature conditions during the early life stages. After spawning in spring and early summer, eggs are fertilized and float near the surface for about 2 months. And then the late stage larvae settle to the bottom during the summer and the early fall. And 15 years ago, field study have suggested that the recruitment of yellowtail flounder in this area is closely related to the ocean bottom temperature and maintenance of a cold pool structure in the mid-Atlantic bight. Just right here. And in fact, there is a seasonal formed cold pool water mass that occurs from late spring to early fall in this area. And so the settlement of the pre-recruits during this cold pool event may represent a bottleneck in the yellowtail flounder life history, during which the local and temporary increase in bottom temperatures impact negatively the survival of the settlers. Recently, modeling studies have also shown that recruitment is closely related to the cold pool dynamics, and especially the cold pool strength, the cold pool intensity. So this yellowtail flounder stock was a good candidate to try to incorporate environmental effect in the stock assessment. So in our project, we have explored 2 questions. The first question was how can we leverage this knowledge, so the cold pool effect on the recruitment, to improve the yellowtail flounder stock assessment. And the second question was, how can this effect of the environment on recruitment be best quantified and integrated? And we have focused on 2 ways to quantify this environmental effect, using observation, which is the most common way to integrate environment into assessment in the Northeast region, and using ocean model, which has not been used or considered for stock assessments, at least in the Northeast region. So, yeah, just an overview about what I'm going to talk today. It's going to be divided into 4 parts. In the first part, we will look at how we built a bottom temperature product to quantify the cold pool dynamics. But this product can also be used for many user applications. In the second part, I will show you how we developed tailored indices that characterize cold pool interannual variations that are associated with the variability of the yellowtail flounder recruitment. Then we will see how we incorporated the cold pool effects on recruitment into a stock assessment model. And finally, I will present some of the results in which we assessed whether including ocean model-based cold pool indices in the model reduce retrospective patterns and improve the skill of short-term forecasts. So in the first part, I'm going to present why we built a bottom temperature product, because we could just use observations or an existing ocean model to quantify the cold pool dynamics, and how we did that. But maybe the first question is, what is the mid-Atlantic cold pool? So as I mentioned before, the cold pool is a seasonal bottom cold water mass below the seasonal thermocline that occurs from late spring to early fall. It's located in the middle and outer shelf of the mid-Atlantic bight, right here. So off the coast of New Jersey and southern New England. There is no clear consensus regarding the origin of the cold pool, even though recent studies led by Xiaomin Chen and colleagues show that the cold pool may have both local and remote origins. So the local origins origin is in fact local remnants of winter water near the Nantucket shore, which becomes isolated from surface due to the summer stratification in the water column. But the cold pool events also originate from a remote source due to upstream cold water sources traveling from the Gulf of Maine, so from the north, during the spring. Different features of the cold pool are very important to the ecology of the region because it provides thermal conditions that retain many groundfish species, and especially the yellowtail flounder settlers, but it also provides an habitat for other species. So two cold pool index were developed to quantify the cold pool intensity. First, there is a method based on bottom temperature observations in fall developed by Tim Miller and colleagues for a study that incorporated the cold pool effect in an age structure stock assessment model in 2016. In this paper, Tim Miller and the co-authors developed a state space stock assessment model, which would become WAM. This is the model we used for this study. And another method was developed by oceanographers based on 3D temperature estimates coming from an ocean model in a study led by Shuomin Chen. These two studies highlighted a large interannual variability of the cold pool in terms of intensity, persistence over time, and volume. So this, the spatial extent of the cold pool. However, these two cold pool indices are not fully relevant for studying the cold pool effects of the yellowtail flounder recruitment and incorporating them into the assessment. So why and what did we need in terms of data to develop such a cold pool index? So we needed temperature at seafloor since the late stage larvae settled to the bottom. We needed data over the period 1972 and to 2018 to match the stock assessment period. We needed bottom temperature during the entire settlement season, so between June and early fall. And the last requirement is about the spatial extent, since environmental data were required to cover the stock area and the cold pool extent. So first, we can look at the limitation of the observation-based cold pool index. So this index is based on bottom temperature observations only in fall, in September and October, while the settlement occurs during the summer and early fall. Also, the high spatiotemporal heterogeneity of observations can be a limitation. So the quality of the index depends on the number of observations each year. As you can see on the maps here, in 2001, a lot of observations are available during the period and the area of interest, here and here. But in contrast, there is a low number of observations in summer and fall for several years. For example, here in 1988 and 89. And moreover, for different reasons, observations are missing for certain years. Recently, for example, the cold pool could not be calculated in 2017 because the fall survey was severely restricted, and it was the same in 2020 because the survey did not take place due to the COVID-19 pandemic. The second index uses ocean model outputs and is based on a strong methodology. It was developed using a ROMS model and can be applied to other ocean models, but it has some limitations too to be used for studying the cold pool effects on the yellowtail flounder recruitment. First, this is a complex method requiring high resolution daily 3D temperature over the mid-Atlantic bight, and it's not easily reproducible. But the main limitation is that the time series do not match the yellowtail flounder assessment period because the index was calculated using a high resolution model, between 1958 to 2007. So yeah, and as I mentioned before, The index can be also calculated using other ocean models, but there is no ocean model on the northeast coast matching the assessment period. And lastly, but maybe more importantly, bottom temperature in ROMS, so the model that is used to calculate this index, is warm biased, especially during the cold pool season. To sum up, both methods have limitations for different reasons. So because of these limitations, we decided to build a bottom temperature product to quantify the cold pool interannual variations that are associated with the variability of the recruitment of the yellowtail flounder stock. So, but more broadly, a high resolution long-term bottom temperature at daily and monthly scale did not exist on the northeast coast and would have been helpful for different applications in which we were involved. So first, we focused on our study area over the stock period, and then, as it worked relatively well, we extended and refined our methodology to the entire continental shelf between 1959 and 2022. So, and to build this product, in fact, we combined 3 ocean models. First, we use a ROMS model. This is the model which is used to estimate the ocean model-based indices that I presented before. This model is a high-resolution model covering the Northwest Atlantic Ocean, as you can see on this map. It has a daily resolution and covers the period 1958-2007. However, as I mentioned earlier, ROMS bottom temperature is warm biased, especially in summer and fall, and the bias varies widely spatially. And I will show you how we did with this in a couple of slides. Then the second source was used is the daily bottom temperature output from GLORIS reanalysis. So it's a global ocean and data estimated in CAST, having a 112-degree resolution, so a good resolution, and covers the period 1993-2019. And which is interesting is that although it's a global ocean product, GLORIS has been shown to be highly representative of observations on the northeast shelf. And the third data source is the daily bottom temperature output from PSY. So this ocean product is based on the same ocean model as GLORIS. So it has the same spatial resolution, and it's also a global product, but it covers a 2 full years time series sliding window. So it can be used to cover the last years of our time series. So the idea is quite simple. We just combined bottom temperature from these 3 products between 1959 to end 2022. For the first part of the time series, we use ROMS, so in green in this figure. Then we used GLORIS in red, and for the period between 2020 and 2022, we use PSY in blue here. But as you can see, the end of the ROMS time series is not consistent with the beginning of the GLORIS time series, and the ROMS bottom temperature was found to be biased. So to reduce this warm bias of the bottom temperature from ROMS, we used the decadal monthly climatologies of observed bottom temperature from the Northwest Atlantic Ocean regional climatology. It provides a high resolution in situ ocean temperature based on a large volume of observed temperature data. So a monthly bias was calculated in each grid cell for each decade over the northeast shelf. Here you can see the mean decadal bias estimates between ROMS and the climatology in summer and winter, which are that are the most and less biased season. So the bias can be very high in some grid cells, especially in summer, and low and even negative in others. And then we used these biases estimated in every grid cell for each month and each decade to bias correct ROMs. Here you can see on the right figure that the bottom temperature time series of ROMs and glories are much more consistent. And we use this combined data set to analyze the long-term trend changes in bottom temperature and calculate environmental indices such as the cold pool index. So the final product, which is a combination of bias-corrected ROMs, glories, and PSY, has a daily resolution between 1959 and 2022. It has a high spatial resolution, and it covers the northeast US shelf. So we presented the methods, the spatiotemporal patterns, and an evaluation of the quality of this product in a paper which was published last month. I'm not going to present this as the result of this paper because it's not the goal of this presentation. But now this product, this bottom temperature product, will be soon publicly available to be used for different applications, from fisheries to marine ecology. It's currently used by a research track assessment of different ground fish stock to identify ecosystem and climate influences. In the Northeast, research track assessment is a process by which the existing stock assessment is evaluated and or improved with new data sets and new methods. We also presented the bottom temperature interannual and seasonal anomalies in the state of the ecosystem reports for the Northeast US shelf. These reports are part of a larger integrated ecosystem assessment approach, and they are developed annually to provide the current status of the Northeast shelf for the New England and Mid-Atlantic Fisheries Management Councils. But this data set can be used for other applications to explore ocean processes, model habitat and species distribution, or to investigate climate influences on population processes. And the first application was our work on the effect of the cold pool on the Yellow-tailed flounder equipment in the Mid-Atlantic Bight. So we developed cold pool indices for exploring the effect of the interannual variations of the cold pool dynamics on the Yellow-tailed flounder equipment. The first step to estimate the cold pool index was to determine the cold pool domain. So we defined the cold pool domain as the area where the average bottom temperature between June and September is below 10 degrees Celsius during the type series. On this map, you can see this area, the cold pool. And then over this domain, we develop not one, but 3 cold pool indices that account for the intensity, the persistence, and the spatial extent of the cold pool. So first, our cold pool index measures the intensity of the cold pool. It was adapted from the cold pool index based on observations I presented previously. You can see here the value of the values of the index each year and the large interannual variability. Then we developed a persistence index that measures the duration of the cold pool. So the cold pool can last a few weeks, some years, but it can also last 3 to 4 months other years. And finally, we developed a spatial extent index to test the hypothesis that yellow-tailed flounder equipment is dependent on the amount of cold pool habitat. So as you can see on these figures, these 3 indices were calculated for each year using bottom temperature from our combined product. It's interesting to note here that the indices show that over the past 64 years, the cold pool has got warmer over time, the duration has got shorter, and the cold pool area has got smaller. So the large interannual variations and these long-term trends of the cold pool dynamics may be important drivers of the yellow-tailed flounder equipment. Then we incorporated these cold pool indices into a stock assessment model to study the cold pool effects of the Yellowtail founder recruitment and the potential consequences for the stock assessment. So in the northeast continental shelf, most of the age-based assessment of groundfish are conducted using the age structure assessment program, ASAP. So it's a traditional age structure model that uses forward computations. In 2016, Tim Miller from the Northeast Fisheries Science from the Northeast Fisheries Science Center with some collaborators developed a state-space age structure assessment model, which have many similarities with ASAP. So the model was initially designed to include environmental effects on population processes, and different papers were published in which they use this model on different case studies in the Northeast shelf. And recently, Tim Miller and Brian Stock and other colleagues have built a general state-space age structure stock assessment framework called WAM, Wodzol Assessment Model. I think many of you already know this model, but WAM is a generalization and extension of the model developed by Tim Miller and colleagues. It's written on R and TMB. And if you want more details on the model, you can visit the GitHub page presenting WAM. There are many helps and tutorials to use and better understand the model structures and all the functionalities. Recently, the Northeast Fisheries Science Center is transitioning from for some stocks from ASAP or VPA, Virtual Population Analysis, to WAM. And WAM was tested and proposed for operational use in different research track assessment, especially for American plaice or Atlantic bluefish. So now I'm going to present briefly the model. So WAM, like ASAP, is an age structure population model. So the model keeps track of the number of individuals of each age in each year, and the transition from a year to another, represented here with the red arrows, are the survival and depends on natural mortality, fishing mortality, and selectivity. And then to find the most likely parameters value, catch and survey data are used. One of the cool things with WAM is that it's possible to incorporate time varying productivity in a flexible way. Basically, there are two different ways in WAM to include time varying productivity. There is random effects, which can account for time varying population dynamic processes without a direct mechanistic link. So these processes can be recruitment, survival, natural mortality, selectivity, and catchability. So environmental variables are not directly included in the model, but it can account for hidden environmental processes that are not directly measured. For example, during the last research track assessment for the American plaice stock on the northeast shelf, they recommended to transition from VPA to WAM, and they incorporated random effects for the number at age, so the survival can change between year and for each age class. The second way to incorporate environmental variables is mechanistic. So you can directly estimate an effect of an environmental variable on the population dynamic process. So environmental variables can be linked with recruitment, natural mortality, or catchability. Tim Miller and colleagues published some example by using WAM in which they mechanistically incorporate environmental variable. They have worked on Georges Bank, on the Georges Bank Atlantic cod stock, and they tied growth and maturity to bottom temperature. Also, in two studies, they have worked on yellowtail flounder stocks, where they have tied call pool and ghost stream to recruitment. And in our work, we extended these approaches. So yeah, we use the one to incorporate the call pool effect into a stock assessment model. So as the southern New England Mid-Atlantic Yodel flounder stock is assessed using ASAP, we could use the same inputs data. Our study area is the yellowtail flounder management area, and we conducted our stock assessment at the same period as the last assessment. Also, WAM can be configured to estimate a large range of assessment models. So for our study, we use specific configuration. So WAM was a full state space model in which numbers at all edges are independent random effects. And the objective of our study was to include the call pool effects. So these effects were incorporated in the Beaverton old stock recruit function. So the recruitment depends on the spawning stock biomass. But WAM allows to integrate differently environmental effects into stock recruit functions, and we tested 3 different ways. Each of the ways to integrate the environmental effects were described in a study of Hills and Beaverton and developed in WAM for a study of Shu and colleagues. In fact, in this study, they determined different types of environmental effects on the recruitment with different underlying ecological assumptions. Specifically, in our project, in our study, we tested 3 ways to integrate the call pool effect into the Beaverton old stock recruit function. First, the call pool can be a limiting factor, where we assume that the call pool affects the carrying capacity by determining the amount of suitable habitats for recruits. You can see on the top figure here, I took from a nice paper of Mander and Thorntons, how the environment can modify the carrying capacity. The call pool can be a masking factor. So in this case, the call pool does not affect the carrying capacity, as you can see here on the middle figures, but it affects the pre-recruit mortality via density-dependent mortality process. And lastly, the call pool can be a controlling factor. So in this case, the call pool affects the mortality rates via density-independent mortality processes. By modifying slightly the structure of the model, we also tested the incorporation of multiple environmental effects on the recruitment in WAM. The incorporation of call pool effects simultaneously allowed us to explore combined effects of the call pool strains, persistence, and spatial extent. For example, a weak call pool event may induce an increase of the density-independent mortality. In other words, act as a controlling factor. And at the same time, a small spatial extent may affect the carrying capacity for pre-recruits as a limiting factor. So now I'm going to talk about the incorporation of the call pool indices in WAM, but it's the same process for the other environmental index. In fact, the call pool indices are not directly included in the model. Instead, they are modeled using state space models with process and observation components. So in the process model, call pool indices are modeled as first-order autoaggressive processes, but it can be also a random walk. And the state space structure implied an observation model to include the call pool indices, which are considered as observation. This structure has the advantage to include observation error and estimate process errors. And also, the model can handle missing values. For example, here on the figure, the black dots represent call pool index observations, and the colored lines is the call pool index estimated by the model with its confidence interval, which is the gray area. And in 2017, here, you can see there is no observation. However, the model has estimated a value associated with a large uncertainty. Yeah, here I'm going to try to summarize our approach. So we tested different models by incorporating successively 4 call-pool indices in the assessment model. We used the 3 indices we developed for this study that were calculated using bottom temperature from the combined ocean model product we built. Each of them describe a specific feature of the call pool, the intensities, the persistence over time, and the spatial extent. We tested also the call pool index based on observations used in 2 previous studies. This index describes the intensity of the call pool based on bottom temperature in fall. So the goal was to test if we have or not the same performance with this index based on observations compared to models with indices based on ocean model products. Moreover, we tested 3 different ways for integrating the call pool effects on the yellowtail flounder recruitment based on different underlying ecological assumptions. So the call pool could be a limiting factor, a masking factor, or a controlling factor. So using the different call pool indices and the different ways to integrate the call pool indices, we fitted 25 WAM models with single call pool effects and combined effects with 2 call pool indices. So here is the 25 models we tested. Of course, I'm not going to describe each line of this table. Just the model are sorted by AIC, and I indicated the models including ocean model-based indices in red and observation-based index in blue. And here the model without environmental effect. There are 2 interesting points here. First, the 24 models, including call pool indices, performed better than the models that did not integrate call pool effects. Second, although the differences in terms of AIC are limited, the 7 best models are those including call pool indices based on ocean model outputs. So overall, the model with ocean model-based indices seem to perform better than the model with observation-based index. And then, based on AIC, 5 models were selected for further analysis. The selected models are represented here. So this included M1, the best peak model with 1 call pool index, and the 2 best models with 2 combined call pool effect. M2, the model with call pool index is associated with the persistence index, and M3, the model in which the call pool index is associated with the spatial extent index. So these 3 models included ocean model-based call pool indices, but we also selected M8, which is the best model including call pool effect based on observations. And finally, we selected the model without any call pool effect as a reference model. So using these the 5 models, we conducted 2 types of analysis. To begin, we looked at the retrospective trends and compared the retrospective patterns over the assessment period. And then we produced 4-year predictions using 2 fishing scenarios. But here I'm going to present only one, the F40%. This is a scenario in which we set the future fishing mortality at which spawning biomass per recruit is 40% of the unfished spawning biomass per recruit. So this is the MSY proxy that is used currently for the stock assessment. And finally, we tested the performance of these models, including ocean model-based call pool indices. So first, we looked at the trends in recruitment and SSB. So the 5 models estimated a very similar recruitment and SSB. over the assessment period. So the incorporation of call pool indices did not modify largely the temporal trends in stock estimates. Next, we wanted to explore the impact of incorporating call pool effects on the retrospective patterns, because it's a major source of uncertainty in the current assessment. So we use the Monroe, which is a classic retrospective pattern metric. So the Monroe are generated through refitting the model to the data after removing its terminal year sequentially, and we did that 7 times. So here in this figure, we represented the changes in Monroe relative to the model without call pool effect for recruitment and SSB. So with these figures, we compared retrospective patterns of models that include call pool indices and the retrospective patterns of the model without call pool effects. You can see on the figure that all the changes are negative, which are the color dots. Thus, the retrospective patterns of recruitment and SSB are reduced when call pool indices are included, and this reduction of retrospective patterns is more pronounced for recruitment than for SSB. You can see the scales on the y-axis are different between recruitment and SSB. And furthermore, the reduction of retrospective patterns is more pronounced with ocean model-based call pool indices, so the dots circle in red here, than with the observation-based index in blue. Then let's have a look at the projections. So the first step for stock projections is to project the 4 call pool indices and their observation errors through 2021 by continuing the autoregressive process model, which is one of the interesting capabilities of WAM. You can see here the projection for the 4 indices. So there are the 3 call pool indices we developed for this study based on ocean model outputs. So the call pool index in green here, the persistence index in the middle figure, and the spatial extent index here, and the call pool index based on observations here in the left panel in blue. So as you can see, there are not major changes in the indices during the 3-year projections. But if we look at the projected recruitment and SSB, we can see that they increased during the projection period. But you can also see differences in recruitment and SSB projection among the 5 models, with higher predicted recruitment and SSB for models including call pool indices, which are the colored lines on the figures, compared to the black line that is the projections. That is the projection for the model without call pool effect. And moreover, the model with observation-based index, so in blue, predicted a larger increase in recruitment and SSB. In this study, more than the short-term production estimates, we were interested in the production performance. So to evaluate the model's ability to provide consistent predictions, we conducted a retrospective prediction pattern analysis. To do that, we generated a series of retrospective predictions for the recruitment and SSB. And for each of the 5 selected models, 15 retrospective 4-year predictions between 2000 and 2014 were generated. So the objective is to compare the retrospective predictions produced by the model that include call pool effects relative to the retrospective predictions produced by the model without any call pool effect. For example, here for the recruitment, we produced a first retrospective oops, sorry. Yeah, here we produce here a first retrospective 4-year productions from 2000 to 2004, and we measured the difference between the projected recruitment in yellow here, and the recruitment when performing the assessment on full data in black. And we measured this difference for the models that included cold pool indices represented in dashed line here, and the model without any cold pool effect, which is the solid line on this figure. And this difference is the mean absolute difference. So then we produced a second retrospective 4-year projections from 2001 to 2005, and we again measured the absolute differences. And we've done this every year until the end of the time series. So you can see the difference between projections of the model with cold pool effect, the dashed line here, and the projections without the cold pool effect. But it's not easy to summarize the results with this kind of figure. So we jointly compared the mean absolute differences with this figure. So the numbers on this heat map are the ratios of mean absolute differences of model, including the model-based indices, compared to the mean absolute difference of the model without environmental index. So here on this figure, the first 3 rows are the ratios for the model with the ocean model-based indices, and the last row represents the model with the observations-based index. And the columns are the projection years. So the first column represents the projection after 1 year, the second column after 2 years, and then 3 and 4 years. So the more red it is, the more the projections are improved compared to the model without environmental effects. You can see on the first column that the ratio of mean absolute differences is well below 1. So that means that the incorporation of cold pool indices substantially improved the recruitment retrospective prediction after 1 year compared to the model without cold pool effect. And as the prediction lead time increased after 2 years and 3 years and even 4 years, the recruitment prediction from the 4 models logically deteriorated. We also found that the models that incorporated the ocean model-based environmental indices, so the first 3 rows here, exhibited better predictive performance than the model that incorporated the observation-based cold pool index here. Now we can look at the same figure for SSB. So again, the more red it is, the more the prediction are improved compared to the model without cold pool effect. By contrast, the SSB retrospective predictions were improved in the second and to a lesser extent in the third prediction years, but the improvement was less pronounced than for the recruitment. And as for the recruitment, we found that SSB prediction improvement is more pronounced for the models that incorporated the ocean model-based cold pool indices. So before concluding, let's focus on the main limitation of this study. One of the limitations is the limited years of observations and the limited number of observations to assess the performance of the ocean products, especially the near real-time product. So it might seem paradoxical since we propose to use ocean models instead of observations because of the scarcity of observations, but it's essential to evaluate the quality of the ocean products, and especially the quality of the global reanalyzed products, which perform well at global scale, but can be biased locally and punctually. To face this issue, currently, a regional model is under development and should be ready soon to support this kind of marine resource applications So this model will have the hindcast and forecast components and could be a good candidate to integrate environment in stock assessments, but also for other applications. In terms of modeling, maybe the main challenges is about the predictive performance. Because in our study, we explore the predictive performance of our models by comparing the retrospective predictions to the estimates when performing the assessment on full data and not to true values. So to evaluate the true bias or the relative error of the prediction for recruitment and SSB, future work should focus on simulation study where we know the true values being estimated. Sorry. Overall, this work we conducted on the southern New England mid-Atlantic yellowtail flounder will be reviewed by the yellowtail flounder research track working group. So research track is one of the major paths for the stock assessment processes on the Northeast coast. So the objective of the research track is to improve the assessment based on new methods, knowledge, and data sets. And then the improved stock assessment can be used for future management track assessment. And the objective of the management track is to provide routine and updated advice to directly inform management actions. So for the yellowtail flounder stock on the Northeast Shelf, the research track working group just started working 2 months ago, and this work will last until 2024. So for this research track, we have several terms of reference to review, in which we will consider several aspects of the work I presented today. In the first term of reference, we will explore the ecosystem and climate influences on the 3 yellowtail flounder stocks. So we will look at the link between recruitment and the call pool for the stock we focused on today, as well as the relationship between seasonal bottom temperature and recruitment for other stocks. And then in some months, we'll work on the stock assessment approach. So as I mentioned earlier, yellowtail flounder stocks on the Northeast Shelf are assessed using the Age Structure Assessment Program, ASAP, and different stock assessment platforms will be considered, including stock synthesis and WAM. In addition to the different studies on the yellowtail flounder using WAM, we could rely on the recent example, and especially the example of the American place. So the research track working group for the American place recommended to transition from VPA to WAM, and they incorporated random effect for the number outage. It could be interesting to use a lesson learned in this research track. We will also explore the incorporation of environmental effects in the selected stock assessment platform through different processes, including the recruitment or the catchability. So the goal will be to test if the inclusion of time-varying processes or direct link to the environment improve the assessment model performance. However, incorporating environmental covariates into stock assessment cannot be considered as a systematic approach, even if an environmental covariate directly affects fish productivity through one of the stock dynamic processes. Incorporating the effect in a stock assessment may not improve management advice and can even provide worse management advice in some cases. This can happen especially when the effect is weak or breaks down over time. The second potential challenge with environmental effect is that when environmental covariates are incorporated in the assessment model, this can lead to significant impact on management decision and short-term catch advice. In the work I presented today, we showed, for example, that we showed large differences in SSB predictions when we included or not environmental covariates, but also when we included covariates based on observations or indices based on ocean models. So it's necessary to be very careful when environmental covariates are integrated. To conclude, our study suggested and confirmed that incorporating cold pool indices into a stock assessment model may improve the yellowtail flounder assessment. We also show that overall ocean model-based environmental data can be efficient and at least as efficient as observations to improve stock assessment. However, skillful temperature incast over the North Sea shelf in near real time or with a few months lag is necessary to be able to incorporate environmental data into stock assessments, operationally. And finally, I would like to conclude this presentation by underlining that close collaboration between ocean modelers and fisheries scientists may be very beneficial, to improve stock assessments. Thank you very much, and I will be more than happy to answer your question or discuss one of these topics.
Thank you, Hubert. That's a great talk. If anyone has any questions, they can drop them in the question box or in the chat. I guess I had a quick question. Do you think the limited performance of the observation cold pool index was because of the spatial extent problems when it was sampled over the years? So it's interesting that it didn't do as well as model-based indices.
Yeah, probably. It's I think it's two things. It's because of the spatial extent, but also I think it's because of the heterogeneity of the spatial extent. I mean, for some years we have a lot of observations in the area of interest across the cold pool, but for other years we have almost no data. So that's why I think we have a best fit with ocean model indices. And the other thing is because the ocean model product we used, the three ocean model product we used have really good quality compared to observations. So I think that's why we have maybe a better performance with ocean products than observations.
Thanks. Do you have any details about that new ocean model that you mentioned? Like, is it going to be like a similar spatial resolution as the ones you used in this research?
Yes. Yes, this is an ocean model based on MOM6. This is a new platform, and many oceanographers work on this platform, and they start developing now new regional products. It's very promising, but on the North Sea shelf, the oceanographic processes are very complex, especially due to the Gulf Stream, the Gulf Stream influences. So it's very difficult to resolve different oceanographic processes. That's why it's a bit long to resolve this problem, to solve the issues. But I think it's very promising because I think compared to the West Coast and to the Alaska region, we don't have a lot of regional skillful regional models here on the Northeast coast here.
Okay. I'm not seeing anything in the chat at the moment, but I will get people a little bit longer to type up stuff.
Maybe I was a bit long here. They all fell asleep.
Do you think there's more interest now in tracking the or developing larger ecosystem models for the Northeast Center now that they're doing those large ecosystem reports? Like, is that one of their research goals?
So, sorry, can you repeat the questions?
Sure. I guess I was just curious if there's a bigger push among researchers at the Northeast Center to develop these ocean models or larger ecosystem models, like you see kind of like the Atlantis and stuff, for the stocks out there now that there's the like, you know, is it yearly or every other year, the ecosystem status report?
Yeah, I think so. Yeah, I think yeah. But the main the main issue, yeah, I think the main issue is the difficulties to develop such kind of model on the Northeast coast. But yeah, there is a big push, especially at the GFDL, the NOAA GFDL, to develop this kind of model to feed the state of the report, and also I think. Since we have a new model, a new assessment model, WAM, now we could consider to incorporate environmental covariates. So I think now we would need like skillful covariates. So observations can be very efficient in some cases, but in others, yeah, skillful ocean models can be interesting when observations are limited.
Yeah, I have a question from Baptiste. He says, what about moving to spatially explicit models? This could be an option. Are there enough data to feed such models in your case?
Yeah, I think, thank you, Baptiste, for this question. Yeah, I think that there are some initiative working on adding spatial dimension, spatial component in WAM. For now, operationally, for example, changes in spatial distribution, for example, for the American place, which is the last research track in the region, they include changes in distribution through VAST. At least they tried through VAST modeling. And then develop like to identify changes in distribution and the most impactful covariates on the distribution, and then they extract indices and they put these indices into the assessment model. But yeah, I think I'm pretty sure that there is some initiative to develop a VAST component directly. But for now, yeah, we don't use this kind of spatially explicit assessment model for assessment.
I have, Baptiste says thank you. Two comments. Melissa says, thank you so much for the excellent seminar. I am thrilled to see this kind of research making its way into management. And then Rachel also says, great talk. And I definitely second Melissa. It's cool to see it get to the research working group stage. Yeah. Well, if there's no more questions, I think we can wrap up. Thank you again, Hubert. This was really interesting.
Thank you very much for inviting me.
All right. Well, and thank you everyone for attending. We will be back in February with another think tank. All right.
Thank you. Bye.
Bye.